same lines as the last one. So just more logic versus set theory. Okay? So let's review a little bit of what we did yesterday. So the main idea was to go logic versus set theory side by side, and they help each other quite a bit. You can see one, you can see the other, and especially the set theory. Mostly one way, but still helpful. So such things as well, we looked into that, the negations for the most part, and how they correspond to complements. So that's one formula we discovered, and it then helps us to understand how to negate propositions. Okay, so there is always a correspondence. It's more than just an analogy, right? Between sets and propositions in logic, but rather there is always, if you're making some statement, there is some set there involved necessarily. So, for example, we can speak of solving a system of equations as statements. In the form of statements. So a function, numbers or two numbers satisfy this equation or that equation. So that those are statements, and they can be true or false depending on x and y. Or we can speak of sets of the same thing. So these are the sets, right? So when we are saying that these statements are satisfied simultaneously at the same time, we put and there. Or we say that we're talking about the intersection of these two sets. Okay, so all go side by side. Okay, so the same with or, that is union. Doesn't happen as often in algebra, but certainly it is a possibility. Here we were talking about, once again, went back to sets. Okay, and the main operations. This one we didn't spend a lot of time on, and that is the empty set to begin with, and secondly the disjoint sets, sets that have no intersection. So what is the correspondence to? What is the corresponding idea in logic? Two sets are disjoint. Okay, so what is the corresponding idea in logic, if you can think of one? So once again, remember, the sets corresponds to propositions. Okay, so this is, how would you translate this? Oh, okay. Let's step back and let's actually maybe talk a little bit about what is the meaning of what is the corresponding idea of the empty set. What corresponds to the empty set in logic? Well, for example, if you're solving a system of equations, okay, and then you conclude that the solution set is empty. Okay, so once again, solution set is empty. What does it mean?
It means there's nothing in the set.
Right. How do you translate it into a statement that does not involve sets? There are no, or better yet, there are, just I want to remove the solution out of this, but there are no x's that satisfy the equations, or equation. Okay, so that's the corresponding statement about sets. So that's the idea. So the empty set, emptiness of the set of solutions corresponds to saying that there is no such x that satisfies the equation. So when I say that x satisfies the equation, what am I saying? What kind of statement is that? So the task is usually in algebra solve an equation. Okay, so but really once the solution has once you went through all the algebra, you make a statement about what the solution set is, and sometimes you point out what that set is. And what you're saying is that these numbers of these are x's. These x's satisfy the equation, okay? Or when there are no such x, okay? So that's the possibility when the solution set is empty. This is the same as to say there are no x's that satisfy the equation. So if I do say that x satisfies the equation, so x satisfies the equation. What kind of statement is that? There are no such x that satisfy the equation, so when I say that some x satisfies the equation, what am I saying? What kind of statement is that? No. No, negation is there's a statement and then you negate it and you don't know, well, the point is it's false. Okay, so the point is the whole thing here is the statement, then you discover that statement is false for no matter what you actually pick. So in other words, the statement in fact, there is an x that such as that x satisfies the equation, that statement is false. Okay, the negative obviously will be true. So that is the meaning of the empty set. Whenever you encounter an empty set with your sets, how does it correspond to logic? And the answer is it is about false statements. Okay, so you can say that A is empty. Okay, or you can say that which will be equivalent to say that there is an x in A. This one is false. So that's the same statement. To say that a set is empty is to say that there is an x in A. That statement is false. Okay, so that will corresponds will encounter once again that becomes an important part of it. Okay, so then the question that I asked a minute ago is what does it mean for two statements to have empty intersection? So now what if A and B are now correspond to, we think of them as statements. Statement A and statement B, how do they relate to each other?
And that right there?
Yeah, well, when the two sets are disjoint, okay, and then the statements are x belongs to A, x belongs to B. Okay, that what do those two statements?
How can they be disjoint by x belong to both of those? Because I thought you said.
Right. So no, that's the definition. So we say that two sets are disjoint when the intersection is empty. Okay. Now what I'm looking for is the analogy or corresponding idea in logic. So this is set theory. What does it correspond to in logic? So we have two statements, and we're asking ourselves about them to be satisfied simultaneously. So I put and between them, right? Okay. So and then well, what am I saying about this statement?
It's false.
That it is false. Yes. So in other words, these two statements cannot be satisfied simultaneously. Maybe one, but not both simultaneously. And there is a good word for it. It is they are mutually exclusive, right? So that's what makes them disjoint is mutually exclusive. So the sets, we say they're disjoint, they're not overlapping, empty intersection, all these good descriptions of this picture. But when you speak of propositions, the propositions are either mutually exclusive. Also, all of the good descriptions are all useful. And you can also say they are contradictory. Two statements are contradictory. So, for example, even and odd, well, you cannot have both. Okay, so either the two intersections, even and odd numbers do not intersect, one way to look at it. Another way to say that two statements, x is even, x is odd, they're contradictory or mutually exclusive. Okay, so that will continue going on. And sometimes you have more than, that's what the example is, sometimes you have more than one statement that is, more than two statements are mutually exclusive. Okay, so this one worked out fairly easily, I suppose, even though it's certainly not obvious what ahead of time what the answer would be. But now I hope you can actually anticipate some of the results. So how the complements, what happens to the complements? That's what we illustrate here. How the complements, what happens to the complement of the intersection? It turns out to be the union of the complements. Okay. in the meantime, and then it corresponds to a logical statement, so the negation of the and will give you the or of the two negations. Okay, so once again, correspondence between sets and propositions. Let's. Did I have an example? Let's think of an example of statements. The sets are illustrated so easily that these pictures are, I think, make sense to use when you visualize things. And then if you remember this, you remember the two pictures at the top as a matter of I guess you got to remember all the pictures. So the complement, the blue complement of the purple, is made of those two sets at the bottom, okay, as the union. So I'm not sure if it is entirely. Is it entirely obvious how the? Let me see. I wonder if I can do. Maybe it's not quite obvious. You see the union now? So I take I make a copy of this, right? So the second one is the complement of B. So this is, I'm holding the complement of B, and I overlap at the complement of A. Okay? And then I'm looking at what's happening. You can see how whatever was still white becomes blue, right? Complement of B above and complement of A below. I put them together. That's what the union is. So whatever is colored with blue counts as the union. Okay, so any element that is colored at least once will belong to the union. And indeed, if I overlap these two carefully like this, I mean, it doesn't look very pretty, but it does give you the picture on the right, the top right. Yeah. Okay, so that's how unions work. Okay. I want to get rid of it. Okay, so once again, so that's the union. Now the statements, once again, the standard example of, if you want to think of statements, how to translate one of the logical laws of logic, like the one at the top, how to translate, or rather the law of sets at the top, how to translate it in the law of propositions of logic next. One is, it's very simple, is just to say replace every set with statement x belongs to A. Okay, so set on the left, proposition on the right. Okay, so and then that statement over here, what does it say? The A stands for x belongs to A. So x belongs to A. Let me write it out. X belongs to A and x belongs to B. Now the negation. And what does it mean? It means that x does not belong to A, or x does not belong to B. Okay, makes sense, right? So it has to not belong to one, or not to belong to the other, in order to not to belong to both of them. Okay. So the examples, that's the standard way of doing, but you certainly can think of specific sets that would have pretty much the same, give you the same example, but something more practical. So once again, if we take, for example, so A is X is a math major, and B is X is a economics major. Okay, then the A and B is X is both math and economics major. And the negative is X is what?
Neither.
No. Either not the other, or one or the other. Right, so he could be math major as long as he's not also an economics major. Okay, is either not math major or economic major. And once again, it's possible to not satisfy both. So it's or that I have over here is inclusive. So we include the possibility that that person is neither math nor economics major. Okay, so that's the left-hand side. Now, if we take the left-hand side of our statement over there, now if I take the right-hand side, I set this aside so that wouldn't be influenced. So I'm just take the formula and see how it works out. So then I proceed. So that's the left-hand side, and now I proceed from this setting to the right-hand side of our equation, and then I have not A is X is not a math major, and not B is X is not an economics major. Okay, and then they're combined together on the right to say that A, B, so it's either one or the other. So it is X is not a math major or not an economics major. Math. Okay, so and then we just compare our conclusions, and if they are related, right? So X is not a math major or not an economics major. That's here, and over there, X is either not a math major or economics major. So it's the same thing. Yeah.
Just, I know that you put the line over it on the right side, but
Yeah.
you used or, and there was an and statement. Like, what? You just because the line's over it. That's why you used or.
Hold on a second. I don't know why did I'm sorry. Yeah, my fault. It's not or here, right? It's and.
I thought it would be or.
No, it's
I thought that was negation, right?
right. No, I messed up something else here. Let's start over here. So we're negating we put the statement A and B together. So A is both math and economics major. Let's say let's let's use logic, use the formula rather than actual our common sense. And let's just to confirm the formula, I want to just do in a kind of a way that is not jumping to conclusions. So I'm negating the statement X is both math and economics major. What's the negative? X is not simultaneously math and economics major. Okay, that doesn't make sense now. Okay, so we're negating the statement X is simultaneously math and economics major. Negative is X is not simultaneously a math and economics major, which turns out to be, another way to say it is that it's if it's he's not one or not the other. Okay, so that's how and translate into or. Yeah, but sorry about that. So there is a meaning. It's not entirely mindless transition from one to the other. But whenever the things are more complicated, that certainly might be very helpful. Okay, so we did some more stuff here. Okay, so that's the, if you start with and then you have or, here you start with or, and you end up with and. So it is, let me try to make that point clearer once again. So as you can see, we're doing intersection. So to do intersection properly, let me erase, using the green color is really not. When you have a union, you need only one color. So here I will be looking into what? I will be looking at an intersection, and for intersection is I will be coloring. I'll use yellow here. So on the right I'll have the complement of B. So this is the complement of B. This is the complement of B, okay. So the point now is that I'm looking for the intersection. So I just want to visualize intersections kind of a dynamical way. So I'll just take this, okay. And then so this is my complement of B in yellow, and then maybe it's not very clear. You see what I'm trying to accomplish? I'm trying to, for the intersection, we only pick those, we choose, we keep only those points that are colored twice. Okay, so so my overlapping doesn't really work as well. Okay, so let me start over. There is a way to do it. Instead of coloring, how about, what is going on here? Okay, how about instead I do what is the right way to put it, is you cannot see through this, so that's the problem. So the intersection is not well visualized here. So this is, let me try again. Where's that thing? Okay, here's what I'm going to do. Just for visualization's sake. Sometimes it's interesting. So I'm gonna not shade it, but well, you'll see what it is. Like this. So complement of A. This is the complement of A. So I'm coloring, but still keeping some of the room left. Okay, so that's complement of A. Now I'm doing complement of B over here, like this. Okay, so hopefully it's clear. And now I do what I did before. I'll visualize the intersection with this way. I'm not sure how clear it is, but we're looking for those points. We want to keep only those points that have double coloring, right? That's what the intersection is. So wherever you see that there is it crossed out simultaneously by green and yellow, that we keep. The rest we throw out. So for example, as you can see, you see those yellow lines inside of A, we throw them out because there is no green there. And similarly, inside of B, there are those green lines, but there are no yellow lines, so we throw them out too. Okay, so the intersection then, as you can see, and then we're left only whatever lies outside of both of them. So as you can see, that green one, we do end up with that green area that we have on the right. Okay, so once again, there is no more point to this than visualization, but some things are in mathematics so abstract that when there is a chance to visualize it, let's visualize it, because it kind of helps to form some ideas, even though they're not very easy to put on paper, but they're helpful nonetheless. Okay, so that's the intersection. Once again, you can illustrate them in the exact same fashion with examples or from numbers. You usually don't solve equations that and then end up with a union, but at least some of the, well, sometimes it does happen. I thought I brought up this example when you have a double inequality. So when, practically speaking, in algebra, when do you encounter something like this? And the answer is you do sometimes say absolute value of x larger than 2. It is a single inequality. Well, actually, how can you interpret this equation? It's so that it's also not made up. We're looking for x's that, that's what this says. Can you, well, if you remember, how do we interpret this inequality? Geometrically.
Yeah.
What's geometric meaning of this inequality? What can you say about x based on this inequality? The absolute value of x, what's the geometric meaning of it?
Greater than 2 and less than
Right, well, you're solving it. What I'm trying to show that there's a point to it, to this equation. It's not entirely made up. Absolute value gives you the distance. So it's a geometric. We are looking for all x's within 2 units from 0. Okay, so not within more than 2 units from 0. Okay, so if you start that way, then the problem you're trying to solve has a geometric meaning. Then you write it algebraically like this, and then the point being, and then you actually end up with 2 inequalities, but they're with or between them. right? Okay, so that these two inequality combined together give you all x's at least 2 units away from the origin. Okay, so that being the point, and then so you do encounter things like that sometimes even in algebra, even though not as often as when you have the union, when you have the intersection. So, and that's how we do it. So the union turns into intersection. Okay, so flipping the conjunctions. Okay, when you negate, you also flip the quantifiers when you negate. And then you do not flip the implication when you negate. So that's the point was made later on. What do you do when you flip the inclusion? And once again, where is it, that statement? Is instead of the negative of A is a subset of B. So that's what we illustrate here is, what is it? The negative of A is a subset of B is what?
There is A that is simultaneously not in B.
Say it again.
There exists an X in A that is simultaneously not in B.
Right. So it is right here, and the standard way to say it is to say this is non-empty intersection. So you may or may not want to speak of a particular element of X, as I did over here, but so this is slightly more compact. You just say that A intersects the complement of B. Okay, so that's that's what we did on the next page here somewhere. Yes, these two complementary things to each other, not complementary. Well, how they negate each other is the inclusion becomes non-empty intersection with the complement. So that's how we do it. That helps us to understand something very important about logic, and that is a mistake made so often that has to be addressed as many times as necessary. So A is a subset of B. Now, it maybe sounds like a silly question. What does it have to do with B is a subset of A? So suppose A is a subset of B. What can we say about the statement B is a subset of A? What?
Yeah, how can A be a subset of B and then you just said B is a subset of A? That doesn't make sense.
Is it well, what you're saying is that they have to be satisfied to be satisfied simultaneously. They would have to be the same. I was going to say that later anyway, but that's a good point. So let me then say it. Two sets are equal. That's the definition. Two sets are equal if A is a subset of B and B is a subset of A.
So if they're equal, they can be a subset of each other. How can it be?
It is called an improper subset. So a set is an improper subset of itself. So it still works. Remember what the definition of a subset is. Every element of A is an element of B. So you are a subset of yourself. Okay. So and then once you understand the inclusion idea, then when do our two sets are equal to each other? When they are both subsets of each other. Okay. So that is frequently is the way you prove. As a matter of fact, you prove things that are two ideas might be equal to each other. Two sets are equal to each other if you demonstrate that every element in A belongs to B, and then turned around and demonstrate that every one in B belongs to A too. Okay, so we'll see that later as well. But here the answer that I was looking for is, well, this is the set B and this is set A. Okay, so proper or improper. I was trying to elicit some kind of a response to the idea that if A is a subset of B, then B is a subset of A, and the answer, of course, not. You cannot. No idea. You're not going to be drawing that conclusion based on this picture or any kind of common sense, right? So A is a subset of B. It has nothing to do with being a subset of A. Okay, so the point of this kind of silly example is to take this what less obvious example, less obvious idea to logic, and the logic is A implies B, B implies A. It's not as silly anymore. That mistake is done to death. This idea you know that A implies B, and then, well, suddenly let's conclude that B implies A. That's done in mathematics and outside of mathematics to death. Okay, so even though, as you can see, that picture on the left is actually demonstrate why this cannot be. You cannot say it's true. You cannot say it's false. A implies B does not tell you anything about whether or not B implies A. It's possible, but you don't know. Okay, so that's the name then. The converse, right? The converse is a statement that technically unrelated to the original statement. So they are unrelated. And if you were doing mathematics, then we're doing one statement. We are not assume that the other statement is somehow appears automatically, even though it does happen. For example, once again, remember the example I have given you. That is the Pythagorean theorem, which is usually stated directly, direct statement. If you have a right triangle, then the a squared plus b squared is equal to c squared. Okay, so that's the direct statement. But then often, well, or less often, the fact is used, which is a converse, and that to say that if you have a triangle that satisfies this equation, that is a right triangle. That's the opposite, and you need two separate proofs. And you never can one take the proof for the statement and then recycle it to prove the converse. Or statements say if a number is divisible by 2 and a number is divisible, what is it? A number is divisible by 4, then it's divisible by 2. Okay, so divisible by 4, then divisible by 2. Okay, so that's a very simple, correct statement. But if you take the converse, it will be simply untrue. And even though, well, so divisible by 2 does not necessarily mean that it is divisible by 4. However, so we just to avoid this very typical mistake in logic, be careful. Often it is well hidden, especially if you need to prove something, and then you tend to jump to conclusions. And then we have the example when it does work out, and that is the contrapositive, which is equivalent to the original. So let's go backwards. So the contrapositive, well, let's say contrapositive, A implies B. What's the contrapositive?
If it's not B, then it's not A.
Not B implies not A. That's right. Not A. Okay, so original. Contrapositive. Let's go backward. Let's use logic to help us with sets. So this is logic. We have, let's make it clear. The relation is, what about the relation between these two statements? A implies B, not B implies A. What's the relation? No relation, right? No relation between a statement and its converse. What's the relation between statement and its contrapositive?
That's a relation, right?
There is a relation there. So what is the relation? It is the same, or you say they're equivalent. It's all good. Two equivalent statements. It's the same statement, pretty much. What? No? Or question? So once again, we did it a few times, so I'm not going to elaborate, and let's go back to sets. What is the idea of, let's translate this into sets. So A subset of B, right? Okay, so we already have a picture. What is the corresponding idea for the contrapositive?
If not
No, it's not F. It will be about negation is replaced with the complement.
You want the contrapositive of that statement, right?
No, we already have a contrapositive. No, I want to take these ideas, which are logical ideas on the right, and translate them into sets. So I already did. I took the first line. So this is logic, and these are sets. So I already took the original statement, A implies B. It is the same as to the corresponding idea as A is a subset of B. The picture is there. What's the corresponding idea for the second statement for the contrapositive? So this way.
B is not a subset of A.
No, no. Remember the negations. Negation of A and negation of B in the last line, they correspond to complements, right? So we're not trying to negate a statement right now. We're just trying to sort of translate the logical statement into a statement of sets. So not B means complement of B. And not A corresponds to complement of A. Set. So A, B statements on the right, propositions on the right, and their sets on the left. Okay, so, and then what the symbol will be what's missing part here?
The same as the one above it.
Yeah, it's the same. It's inclusion. Okay, so just let's look at the statement. Not the statement, but this inclusion. Does it make sense to you? If it doesn't, it is good news because then we're discovering something new. From logic, we discover something about sets.
So you're saying X does not belong to B as a subset of X does not.
No, the complement, whatever X, whatever element X, little x, does not belong to B, then it also does not belong to A.
But that's a subset symbol.
It is.
So you didn't say subset anywhere in that statement.
Subsets can all be translated into elements. So X, let me do that. X belongs to, restating, X minus B implies that X belongs to X minus A. Right? Oops. So that's what the meaning of one set is included into the other. It means that if X belongs to the first set, then it belongs to the second set as well. Right? So this is my X over here. As you can see, the smallest set is A, the biggest set is B. If X is inside of A, it will have to belong to A. But then the same thing applies to the complements as well. It applies to any pair of sets. So if X belongs to the complement of B, it belongs to the complement of A. It might not be obvious. That's why I want to make a picture here. So this is A and this is B, and this is X. Okay, so let's just plot. As you can see, big B is bigger than A. B, A. Okay, so, and one more time. B and A. Okay, let's plot the complement of B. The complement of B is this. Right? And this is the complement of A. Right? So what's the relation between them? No. Well, look, compare these two sets, the purple and the green. What's the relation between them?
B is a subset of A.
A is not colored in both of them.
No. One is bigger than the other.
Yeah.
One is bigger than the other. This one is bigger than the other. It includes, the green one includes the purple one. Right?
B would be a subset of A. Or
No, A is a subset of B. Look at the picture. A is a subset of B. Right? That if you ignore the color, A is a subset of B. But with the color, I did what I colored was the complements. So I complement the B, which gave me that purple one. I colored the complement of A, which is green, and you can clearly see which one is bigger, which one includes the other. So how everything reverses, because if A was smaller than B, well, you take the complement, it's the exact opposite relation. Okay, so and that what we just discovered on this picture. This is what we see here. Complement of X is a subset of complement of A. Okay, so the inclusion reverses. The inclusion reverses when we do contrapositive. It's the same statement. These two are the same. Once again, just these were two equivalent statements. These are also equivalent. A is a subset of B, and complement of B is a subset of complement of A. It is the same statement to say. Okay, and that's what picture demonstrates. Okay. Okay, so like I said, it was a logical idea that we translate into sets, and it also takes this very tangible form. So this is the that picture at the bottom is illustration of that logical is the logic of contrapositive. Remember, so once again, these two statement and its contrapositive are equivalent to each other. So they're either simultaneously true or simultaneously false. So and why? That's the explanation. Either one moving from sets to complements reverses the arrow, so that will make sets what was small became bigger, and therefore the inclusion is reversed. And that is why we'll never forget, I hope, to when we do contrapositive, not to forget to reverse the arrow. So if it was from A to B, if now we're talking about the negatives, it is reversed. If you want the same statement. If you want a converse, that is a totally separate idea, and then as you can see, there is no negation. The converse idea has nothing to do with negations. It is about reversing implication period, or reversing inclusion period. And then what it brings us to, so back to converse. So I hope the contrapositive is, this picture will put it to rest, to just remember it is the same statement, just into different forms. And this is its illustration. Contrapositive is very important, but so is converse. Let's look at converse first. We already started down that road, and that is A implies B, B implies A. Together, taking that statement, take it together, we know what it means. A implies B, B implies A. Well, think about sets. A subset of B and B subset of A, we know what it means. A equals B. So two identical sets. The same with statements. If A implies B, B implies A, they're equivalent. They are either simultaneously true or simultaneously wrong. So that we're going to use a lot. So statements that are equivalent and one is replaced can be replaced with the other. So with two sets, you may have two different representations of the same set, but maybe one is somehow better, takes us in the direction that we are heading, and we replace one with the other. Same with logic. We're trying to do proofs or analysis, and once again, it is the safest. When you go from A to B, even though A does imply B, you might be losing some information. It's like to say, how about x larger than 3, then x is larger than 2. Is this a correct statement? Yes. But you might be losing information. So if you forget where you started, you might be losing information, and you have. But when you do it with equivalent statement, then you are knowing that you can proceed. You have made a replacement, and then you don't have to go back and check out that everything is correct. That's why solving equations or inequalities sometimes it is the safest way is to do it in this way. So replacing statements one at a time with its equivalent. So you don't have to retrace your steps. But that never works out outside of some elementary algebra. We do have to proceed in this fashion, and this is the maybe I have something else to mention before. we're getting to proofs. You know, although we have talked about propositions, what we do with them, how to combine them together, how to determine which one is true, which false, but really what we care about ultimately is proofs. And so how do we use this to do proofs? And the idea is, as I indicated, what we usually try to do is, what does a proof typically look like? Prove, or a theorem, prove a theorem, A implies B. So a number is divisible by 4, then it is divisible by 2. Okay, so that's an example of what we want to prove. Okay, so then it is very simple, and there is really no challenge. Well, let's do it anyway. So theorem: if x is divisible by 4, then x is divisible by 2. Okay, so just to illustrate the ideas, and then the challenge is really to apply the same ideas of logic to proofs that also have some other challenges. So okay, so let's prove it quickly. So how do we do it? We have one statement, we have one to apply the other. Usually it might be, sometimes, not in this case, this is actually fairly simple. So say from C to, I don't know, from A to A1 to A2, it might be a long sequence of implications. With the end, we have that B that we care about. Okay. In this particular case, the proof is entirely direct, so we should be able to prove it in with nothing but one step. Okay, but remember what we always start with: definition. So we start with the definition. I don't want to do analysis. I want to go straight to the proof, as it is a one-step proof. But you have to, if you want to write it carefully, what you say is by definition, x is divisible by 4 when what? X is equal to 4m, where m is some integer. Okay? If you want to anticipate what's going to happen at the end, well, so I want to conclude that x is divisible by 2, so let me use the same idea and put it here. By definition, x is divisible by 2 when x is equal to n, where n is an integer. So all we need to do now with these two definitions in place, in fact that's the end of the proof, I have to connect these two. That's the one big implication. I have to explain that implication. So can you make that final link? So let me underline this statement and that statement. So we need to get from one to the other. So the first statement is taken for granted as the truth, so x has been represented as 4m where m is some integer. So how do we need to get to that one? So m is known. No, it's not known, but it is assumed to be given, and we need to find n.
Set 4m equal to 2.
That's right. So this is how we do it. Let n equal to 2 m. Yes. Okay. Then x is equal to 4m is equal to 2m, right? 2n. Then, right? Okay, so we algebraically connected these two statements. So the implication is proven. What we're going to do next time is a contrapositive way, so backwards, right? So we'll start with the negation of the conclusion and walk our way backwards. Okay.
When will the homework be?
Same Friday night.
Friday. Okay.
Okay.